Hey everyone, it's Mr. Oliver again. I'm going to go over the Unit 3 review practice for response question number 2. So let's get to it. All right, so in this question, once again, we need to read the question carefully. And we have two metal spheres, so it's important that they're metal, that are far apart compared to their size and that are held in place. So they're far apart, so they don't really interact with each other physically. And they're held in place, so they're locked in place somewhere. The spheres are connected by wires to either side of switch S. So there's a wire connected here, and there's a wire connected here between the two. Initially, the switch is open. Sphere 1 has mass 1, radius 1, and a net positive charge, positive Q naught. Sphere 2 has mass 2 and radius R2 smaller than R1. So this is a small sphere, this is a large sphere, and is initially uncharged. So it doesn't mean it's devoid of charge, it just means that it's electrically neutral. So Q2 is 0. All right. The switch is then closed. Afterwards, so what happens whenever you close the switch? Well, what has to happen is the system has to reach an equilibrium condition. In other words, it doesn't like imbalance, and because they're connected by wires and they're both metal, charges can kind of even out with each other. Okay? And so ideally what would happen is whatever sphere you have on this one, or whatever charge you have on this sphere, will redistribute itself on the sphere 2. So for instance, let's say that this left sphere had a charge Q naught equaled 10 coulombs. That's a lot of charge, but let's just assume that. Well, after you close that switch, what will happen is the charge on the right will not be 0. It's going to share charge between the two spheres. It's going to have some amount of charge on the left that was a portion of the original. So Q2 now will be some proportion, some percentage of Q naught, right? And that percentage kind of depends on the physical situation. We'll get to that later. All right. Maybe it's equal. Maybe this one gets 2/3 of the original charge. Who knows? All right. So let's go ahead and calculate. Let's go ahead and answer what happens. Oh, it says afterwards sphere 1 has charge Q1. Okay, yeah. So this is going to be now Q1 after you close the switch. This will be Q2. Q1 is at potential V1. The net electric field strength outside its surface is E1. And then similar terms for the second one. Okay, so for this first question, it says indicate whether V1 is larger than, smaller than, or equal to V2. In other words, does the voltage on the sphere 1 compare equally, greater than, or less than this voltage on sphere 2? Explain your reasoning using appropriate physics principles and or mathematical models. All right, so here's the solution for part AI. The solution is V1 equals V2. They both have the same electric potential. So the reasoning for this is that when the switch is closed, charge will naturally flow in an effort to reach the equilibrium state. Okay, so charges, and I'm going to abbreviate this with bullet points. Charges try to reach equilibrium. Remember, equilibrium is a state where the net force on all the particles is equal to 0. That's what's trying to happen, is it's trying to reach this lowest state of equilibrium, right? And so what happens in that case, is it's trying to balance the energy. It's trying to make one object have the same amount of energy as the other, okay? And so what's happening is it's trying to have the charges try to redistribute, so no potential difference in other words, delta V exists. Because anytime there's a potential difference, it means that one object has more charge than the other, and it doesn't like that for that to happen. All right, and so when they do reach equilibrium, the spheres are essentially one conductor. let's say the sphere system acts as one conductor because they're both metals while they're both conductors. All right, and that's the solution for part AI, or AI. For AII, the question says, indicate whether Q1 is larger than, smaller than, or equal to Q2. Explain your reasoning. All right, so in this case, you need to kind of think about the physical size of these two spheres. If you think about it, the spheres are going to be deposited on the metal surfaces. And sphere 1 has a surface area that's way larger than sphere 2. And so if you think about it in terms of, like, let's say it was like a capacitor or something, the bigger the storage device, the more charge you can store on it. And for this question, that's really all you need to say, is that Q1 must be greater than Q2, since the larger sphere has more surface area than the smaller one. It must hold more charge. Don't use the word it. Say charge sphere 1. I cannot write. Sphere 1 must hold more charge. Okay, and that's all you need. Now for question A, I, the third I, the question asks, indicate whether E1 is larger than, smaller than, or equal to E2. And guys, what we're talking about is the electric field right at the surface. So like this would be like E1 right here, and then somewhere else E2 over here. And they're far enough apart to where these two E's don't interact. These two electric fields don't interact. So in this case, this is a little bit harder to describe. So I'll state the answer. E1 is going to be less than E2. Okay. Some of the facts of this is that smaller, more compact objects, smaller, more compact objects, let's call these conducting objects, due to the smaller, more compact conducting objects must have stronger fields due to the charge density. Okay, so what's a good way to show this? All right, well, we never talked about charge density. We didn't talk about Gauss's law. There's none of these other kind of things. But the one fact that we do know, and something that you can use, is an expression for the electric field. And that's going to be KQ over R squared. That was our expression for electric field for any kind of a sphere, a point, or something like that. So let's just do a sample calculation. I think that's the easiest. So let's do this. Let's let Q1 equal 2 nanocoulombs and R1 equal 2 meters. Okay, and then let's also do a similar thing for Q2. Let's let Q2 equal 1 nanocoulomb, because we said earlier that it actually let's do, hang on, yeah, let's let Q2, because we said it has to be smaller, be 1 nanocoulomb, and Q2 is also smaller than Q1 because of the picture. The radius is smaller. So let's say the radius of the second object, R2, is equal to, I've got my numbers all messed up here. Q1 is greater than Q2, and and R1 is greater than R2. Okay, so let's say that this, yeah, let's say that Q2 is 1 meter. Okay, so we're just making up some numbers here. All right, so for charge number 1, we can calculate an electric field. E1 is equal to our Coulomb constant K times our charge, which would be 2e minus 9, divided by the radius squared, so 2 squared. And when we do this calculation, we get 4.495 newtons per coulomb. Okay. For charge number 2, the electric field will be K times 1e minus 9 divided by 1 squared. And when you do that calculation, you get 8.99 newtons per coulomb. So sure enough, the electric field on the smaller one is bigger in magnitude than the electric field for the larger sphere. And if you think about it like in terms of area, the surface area of a sphere varies by the square of the radius, right? If you don't remember, for a sphere, area is 4 pi r squared. And the bigger the area, or the bigger the radius, the bigger the area, that charge is now distributed more thinly across the surface. And because that squared term is more dominant than the charge term, because right here we've got a squared term which is more dominant than the charge term, that squared term is going to be more effective. And so the electric field on smaller, more compact objects always has to be stronger in magnitude than ones that are larger, regardless of what happens. And that's just kind of a good rule of thumb. Okay. All right, so that's all the question for number A. So for B, it asks, the distance between the centers of sphere 1 and sphere 2 is D. The switch is now open, the wires are disconnected, and the spheres are released, all without changing the charges on the spheres. Write a paragraph that describes the velocities of the two spheres after they've been released, as well as any interactions. Whenever it says interactions, it's talking about forces. So any forces they may have on each other. Explain how their movement changes the longer the time progresses from the moment they were released. Be sure to explain why the spheres act as they do using proper physics principles and reasoning. All right, so what you need to do, this is kind of a long drawn out thing, so I'm just going to try to bullet point this. All right, so first of all, in this scenario, when they're connected and they come together, it says the spheres are released all without changing the charges. Okay, so they still have similar charge. They're both positive, in other words. So the sphere on the left is a positive charge, but remember, it's got a bigger charge than the charge on the right. They're still both positive. Okay. Now, what's going to happen is they're going to repel. So the very first thing you need to do is they say they repel because of they're both positively charged. Okay. All right. And that's due to the Coulomb force. So you'd probably want to make some kind of statement about the Coulomb force. All right. Now, that Coulomb force is actually equal because of Newton's third law, equal and opposite reaction. So charge 1 pushes to the right, and then charge 2 pushes to the left with equal magnitudes. Now, the result is going to be different because they have different masses and different charges, but the force itself is going to be the same. All right. So that means that sphere 1, I'm just going to abbreviate, sphere 1 accelerates left, and you need to use the word accelerates left. And sphere 2 accelerates right. Okay. Now, due to sphere 1 having a larger mass, it will accelerate at a slower rate. So this acceleration, A1, is going to be less than A2 due to masses, due to their masses. Okay. The reason, if you want to make a reason for this, due to the masses and Newton's second law. you could say something like the acceleration of sphere 1 will be less than the acceleration due to acceleration of sphere 2 due to Newton's second law and how acceleration is inversely proportional to mass, something like that. As the spheres move apart, the separation distance increases. So it's important to say that the separation distance increases. They get farther apart, right? This means that the repulsive force will decrease as time progresses. So the force decreases as time goes on. So what that means is that the acceleration does as well, because force equals ma. So if the force decreases, therefore a acceleration does as well. All right. Eventually, the force and acceleration approach zero. It never will actually reach it over time, but infinitely far away, you can essentially say that the force is zero. Mathematically, it does have an asymptote at zero, but it's okay to say it goes to zero. As far as the velocity goes, the spheres start at rest, so that's something else you need to say. They start at rest. Okay, start at rest. And speed up, moving left or right for sphere 1 or sphere 2. Start at rest and speed up, moving left. Sphere 1 moves left and moving right. Sphere 2 moves right. All right. However, as the spheres separate, this velocity will increase, but at an ever diminishing rate. So the speeds increase, but eventually leveling off. And the reason why is because A approaches zero. Both spheres will, over time, the acceleration becomes zero, and so therefore you can no longer speed them up anymore. It's just going to reach, the speeds are going to reach some kind of constant final velocity. All right. Now, that's essentially all you need to state. Now, you need to say it in a paragraph with proper grammar and sentence structure. So let me read that off to you real quick, what I wrote. I said, because both spheres have the same charge, or have charges positive, they will repel due to the Coulomb force, which is equal on both spheres. This will cause sphere 1 to be accelerated left, and sphere 2 will accelerate right. Due to sphere 1 having a larger mass, it will accelerate at a slower rate than sphere 2. This is due to Newton's second law. In other words, acceleration is inversely related to mass. As the spheres move apart, the separation distance increases. This means the repulsive force also decreases. Because the repulsive force decreases, so does the acceleration. Eventually, the force and acceleration will approach zero. As far as the velocity goes, the spheres start from rest and speed up, moving left for sphere 1 and right for sphere 2. However, as the spheres separate, this velocity will increase, but at an ever diminishing rate. Eventually, they will both reach some maximum velocity and continue on that maximum constant velocity forever. And that's it. Okay, so I also went ahead and sketched out what the acceleration and velocity graphs look like. Acceleration versus time would start off at some maximum value, and it would kind of decay. It'd have some kind of, not really an exponential decay, but it kind of levels off towards zero. And then the velocity graph is kind of the opposite of that. The velocity starts at 0 and then levels off with some kind of horizontal asymptote, something like that. That wasn't requested on the problem. But anyway, that's the solution for part B. If you have any questions or need any more clarification on that, just shoot me an email and I'll be glad to help you out. Thanks a lot, guys. Bye-bye.